Actually, I do have one, but that is upstairs.
Yeah, so they have a one here. Let's say.
Actually, I forgot to. Anyway, yeah. All right, so I think we should get started. We're already a little behind. So first of all, it's a great pleasure to have Professor Mingyi Hong from University of Minnesota to give us a talk today. Mingyi is a great friend and a top researcher in machine learning. Let me first briefly, give a brief introduction. Mingyi Hong received his PhD from University of Virginia in 2011. He's currently associate professor in the EC department at Minnesota. His research has been focused on developing optimization theory algorithms for applications in signal processing and machine learning. So he has lots of outstanding awards. The most recent one being, this 2022 Piers Simon Laplace Early Career Technical Achievement Award from the IEEE Signal Processing Society. So without further ado, let's welcome Professor Mingyi Hong.
Very nice introduction. Thank you for everyone being here. This is my first time in Columbus in Ohio State, so enjoy the weather here and then very nice campus as well. So today I'm going to talk about some of our recent work on applying optimization technique for large language model. So for myself, I think my background is similar to everyone here. Is in ECE and then signal processing, networking, wireless communication are very dear to my heart. But then for me, I'm more focused on optimization side of it, developing algorithms and so on. So, okay, so in this talk, I'm going to sort of try to relate how techniques in optimization can be used to improve foundation models, especially fine tuning or some pre-training tasks. So this is a joint work with my students and postdoc. So Xinwei is my former students, now is in USC for postdoc, and these are my students. And then my collaborators, and then also collaborators from industry as well. So these will be mostly based on some of our recent works on either optimization literature or NeurIPS, and a couple recent works that hasn't been published that's been made online. Now, before I start, I want to have an advertisement. So this year we have a Midwest Machine Learning Symposium. This year's version is in Minneapolis. So it will be May 20 to 21st. So we have about 20 invited speakers, and Kevin here also has helped us identify 2 people in Ohio State. We'll have four keynotes and panels and so on. So the registration is free, and then we'll provide free student housing, and then travel awards and so on, right? So everyone, if you're interested, please take a look, and then everyone's welcome to join. Okay. So that's that. Now let's begin. So since the topic of today's talk is about foundation models, let me say a little bit about it. So I think everyone knows what foundation model is. Basically, those are models that's being trained on using many hours of GPU hours and then lots of data, right? So they were able to fine tune to different tasks, right? So the most well-known foundation models are probably ChatGPT, GPT 3.5, 4, also Vision, VIT, Vision Foundation models. And also there are many different, I think many foundation models have been coming up for geology, for many other different things, right? Diffusion models. So in particular, of course, language model are one sort of big area here. This is sort of the evolution of foundation models in the LLM. Even like 5-6 years ago, there's nothing before that, but then like everything has been grown really rapidly, right? So the Google, Meta, OpenAI, of course, are involved in all this. And then, of course, here, this is the OpenAI's GPT-4, GPT version of foundation models. So the main question I want to ask here is what can researchers from our background, or at least my background, right? So optimization, signal processing, communication, networking, can sort of contribute or benefit from, let's say, or contribute to the foundation model research. So I think there are mainly two ways, right? So one is that we use those to apply to our own applications. So there are certainly foundation models for wireless communication that's this is up in discussion. So you can use these models to optimize beamformers, let's say, right? So to decide network schedule, things like that. Also, there are foundation models for medical imaging. I was talking to Phil this morning. They were using diffusion models for recovery, right? And also for solving operation research problems, right? So you have very hard optimization research problem. So typically what people do is that you translate the problem statement to using foundation model to translate it to something that is understandable by a solver, and then you use solver to put the result, and then then you use the foundation model again to interpret the result, right? So those are sort of how you apply this, how we can apply this for our own research area. And on the other hand, this is a second thread, which is try to use the modeling and algorithmic tools that we have in different areas, but try to see if we could define new problems or solve challenging problems over there, right? So I'm going to mostly focus over there for the second application, and that's as well the second thread, and then discuss a few of our works on the related topic. So let's see how much I can cover, but those are the things that I sort of had in the slide. The first is I want to use, so we'll use bi-level optimization, which is a particular optimization problem that you guys will see later. And inverse reinforcement learning for aligning large language models for with human preference, right? So here, this application is basically fine-tuning language model so that they can be more aligned to what we like, right? So that's one application. It turns out that this problem itself is can be cast into a sort of inverse reinforcement learning problem, and then it can be solved very efficiently. The second application is that we'll use zero-shoulder optimization, which is an optimization methods where you don't need gradient. You only use forward pass. You only need to evaluate the loss function for the value of the loss function. So you use those, we use those kind of technique to minimize or to reduce the memory consumption for fine-tuning language models, right? So this is the second application. The third application is try to understand how, so both of these are fine-tuning. So this means if your model has already been trained using lots of data, but then I want to fine-tune to different tasks. The third one is more related to the previous step, which is the pre-training. So here the question is, how can I make the pre-training more private, meaning not leaking information, private information. So over there, we need to sort of design algorithms, design training strategies to make it differentially private. Okay, so we'll also discuss what differential privacy is and so on later. But overall, the goal is to demonstrate that the critical role of a principled optimization modeling and algorithm design in sort of in advancing the state of art of AI systems. Okay. All right. Any questions before I? Okay. All right. Thank you. All right. So first of all, we'll talk about the first topic, right? So we'll begin by discussing the connection between an important problem in large language model training, which is the sort of a model and human alignment problem. Typically, people would just call it alignment problem, and a classical problem called inverse reinforcement learning, right? So we'll see how these two are related and how we design algorithms for this and how we apply to that area. So the key question here is how to formally formulate this so-called alignment problem and develop algorithms and which are superior compared to the popular heuristics. So to introduce the alignment problem, so there are a few steps here. So the assumption here is that you already have a pre-trained model, which has consumed a lot of data and which is being trained on standard NLP tasks like mass language modeling, right? All right, so you have this model, but then this model cannot be directly used because it doesn't know the human preference. That meaning if you ask an inappropriate question, it may repeat some inappropriate answers. So you want to avoid those, for example. Or typically we want the model to give you a particular style that you want, right? So those are sort of human preferences that we want the model to align to. And then, so in order to fine tune the language model to align with human preference, there's standard approach. There are three steps. First step, it is called supervised fine tuning, SFT. What people do is to collect demonstration data, X and Y. So X here is a prompt, is a question. Y here is the answer. So these are sort of human expert provided demonstration data, high quality, telling the language model for this kind of question, what should answer, right? What's your answer should be, and then train in a supervised model from this from pre-trained model. This is step one. All right. So step two, I use a different set of data. This is called reward model training. In this step, what people do is to collect comparison data. Right. So you have a prompt, but then you have two different responses. One win, one lose. Win means I prefer this one. Lose L means I do not prefer this one. Right. And then so this y greater than YL means this is preferred than the other. Then we train a reward model based on this comparison data, right? So this provide different perspective compared with only the positive signal. Here they also have negative signals, which I don't like, right? And then I train a reward model, which is able to tell, given X and Y, how likely human will like this and not like this, right? They'll give a score. So once the reward model is trained, you will further fine tune the model based on here, further fine tune the model using a reinforcement learning policy optimization, right? So three steps together, you'll basically tune the reward model, tune the language model once and train the language model twice. And then finally, this will be the sort of aligned model that will be finally produced, right? So this is typically the final stage before a language model is released, right? So after this, you can use it, right? Okay. So this is called the alignment problem. Now, just to give you an example, what is SFT data? So for example, you're solving this problem, right? So 2x plus 3 equals to 7 for x, and then you're solving this. So for SFT data, I simply give a correct answer. For the preference data, you'll give two answers. I don't need to read all this. This is a correct answer basically, but then you have a correct step-by-step approaches. This one, this is not preferred answer. Sometimes it could be just completely wrong, or it could be that it just simply give you a correct answer, but there's no step, right? So this is also not the thing you prefer. For example, now if you ask ChatGPT, hey, give me answer to some question, they will always typically give you step 1, 2, 3, 4, all this. So this is a style that is preferred. So you need to instill that style during this process, right? So there's a preferred, non-preferred, right? So this is the preference data. So you see that the preference data is more diverse in the sense that you need to compare with all different cases and then tell the model that which one's better, where's the hierarchy. Here, I'm only telling you, hey, you should do this. Okay. So these are different kinds of data, and therefore you need a different ways to do it. So, and then this is basically the 3 step I just mentioned. So this is just a graphical illustration of these steps. Now, a little bit more mathematical expression for different steps. Well, the first step, given a demonstration data set, d little d, right, demonstration. So what you do is to solve this problem. What this is sorry, this should be pi. Pi xy here is basically the language model, right? So given x, what's the probability of outputting a y, right? So this is a probability policy. So we call it policy or language model. So given this policy, right? So I want to maximize the likelihood of this policy, the given X, the likelihood of this policy will matching the expert data set, right? So this is a maximal likelihood problem. Although right is minimize the minus thing, right? So this is a sort of a typical supervised learning problem in language model. Now, in the second stage of the reward modeling, now you're given a different set of data, so you can no longer do this. But I need to encode the preference. So what people do is to train, to optimize this loss function, which is minus. So basically maximize this, right? So here is a log. Sigma is the sigmoid function. And then here you have a reward function minus a reward. So the reward evaluated at the preferred data minus the reward evaluated at the not preferred data, right? So I want to maximize the difference between the two. I want to make sure that you could distinguish between the two. And then theta here is the parameter you'll be able to train. So this reward model is different than this. Okay, this is your final language model. This is a reward model, something that is extra.
So are these YWYL humanly labeled or?
Yes, human label. So the generation of YW and YL could be automatically generated, but then you should be able to rank it. So typically it's a human rank, but nowadays, in many cases now, you also ask the ChatGPT or GPT-4 to rank it. In many cases, because it's more efficient. But those are ranked. And then the final step is the policy optimization, right? So once you have the reward, now this reward model supposedly will be able to provide a score for preferred or non-preferred continuation, whichever you see it, whenever you see it. Then you will use this reward model to further fine-tune pi. So here is the policy optimization. So given the reward model, now this R is a fixed, you are maximizing, so you're maximizing this reward minus a loss, a sort of a penalty, okay? But so you try to find, you're maximizing the pi here, you try to maximize the pi so that the Y as generated from the pi has high reward. So you can ignore this, right? So this is just a regularizer, doesn't matter. So you're generating, you try to find a policy such that given X, you're generating Y, and then this XY pair is highly rewarding, right? So this is a reinforcement learning problem, right? Because your optimization parameter is in the sort of a distribution, right? You optimize the distribution, so generation. So this is called policy optimization. So you see that again, so pi is optimized once and twice, right? So this is the sort of a standard way that people are optimizing this. There are a number of major drawbacks here. So first of all, there's a lack of formulation and theory, right? So we know that these are the steps that people do, but what is the alignment problem you're really solving? There's no single problem. So for us, and at least for me, I want to see a problem that you're solving and design an algorithm. It's not like just give me steps and this is what you do. So there's a lack of formulation. Then if you don't have formulation, then there's no theory. I don't know what problem I'm solving. So in particular, why the alignment problem has to be separated into these three stages, right? So this seems to come out of nowhere, right? So this is pretty heuristic. Second is a pool data utilization, right? So you see, only the preference data is used in this step, right? So this step, you only use the demonstration. Here, you only use the preference. So now, if there is some heterogeneity among the data, for example, your preference data is low quality, or it didn't cover certain areas, then the reward you train, because it only sees the preference data, will be bad. Therefore, the final step will also be bad, right? So because it's a stage-wise, right? So later stage never see the data in the previous stage, right? So there's a potentially pool data utilization, and then also there's a lack of explainability. So what is the problem? What is the problem actually solving, right? So what is the reward that you're learning? Again, this is because of a lack of a problem formulation. So I want to start with a problem called joint reward learning and policy optimization. Try to formulate the problem more rigorously. At the beginning, we'll only show how demonstration data is used. When only demonstration data is available. And then we'll try to formulate the problem, try to discuss algorithms, try to connect this with the optimization problem. And then we'll extend this approach to leverage both demonstration and preference data. In the end, you'll see that it can formulate the entire thing into a single problem. And then you can develop whichever algorithm you want to solve. Okay, so this is the plan. All right, any questions? All right, so, okay, so the problem, so when I see the problem, I actually saw this as a so-called inverse reinforcement learning problem, right? So I will explain what that problem is. So this problem, it's a very classical problem in RL or even in economics. So a learner observes a Markov decision process generated by an expert completing certain tasks, right? So this task could be could be driving the car, could be manipulating, or could be trading, right? So you have an agent that is doing something like this, expert. So you collect those data. The question here is based on the demonstration data, how to infer the expert's reward model, why he was doing this, he or she is doing this, as well as to find a good policy, right? So this is called inverse reinforcement learning because I'm inversely inferring the reward model as well. So in this setting of training, so you can see that this statement is already pretty close to what I just said. Just to make it a little bit more concrete, in a setting of training LLMs, we have the following correspondence. So the demonstration data in LLM is, demonstration data here is the supervised fine-tuning data, right? So it's a positive signal. The optimal policy here is the aligned language model. And the reward of the expert that you try to learn here is the reward model that you learned in the previous stage, right? So there is a very close relationship between these two problems. So we'll start with here, right? So as we know, reinforcement learning problem itself is a little bit different, right? So it's given a reward function, try to find an optimal policy. Inverse is you need to find both, and we know from the literature of RL that if you can learn the reward function of an expert well, there's many things you could do. For example, it could perform counterfactual analysis because you're understanding why the agent is making the decision. It can also transfer easier to other different cases, right? And most recently, this AI alignment problem, it's also something somehow related. So the basic setting here is this. So you give an expert trajectory. This is D, data D. Assume the learner is able to access the environment because you're playing. So this is a reinforcement learning problem. So you have state and action, and then you need to transition, right? So you need to involve the environment. And then you have a inverse reinforcement learning algorithm. You want to identify both R and pi. R is the reward, pi is the policy. Even the notation is the same, R and pi. So besides language models, the people also using RL for self-driving, right? So in this case, the expert data is a human driver behavior. You observe in a human, and then you want the system to learn the policy, which is automatic driving. Right? So this is actually, so one of my collaborators is collaborating with Waymo for this, using this kind of approach, right? So they actually use this kind of approach as well. So there's a a lot of literature on inverse reinforcement learning. I'm only going to briefly discuss something after 2000, but there are many things before that too. So classical study typically focus on linear reward setting. And then I'll provide the setting later. More recent work has been focused on nonlinear reward parameterization, but the computation is very, very heavy. Okay, so the contribution of this work in terms of inverse reinforcement learning is that we provide a new formulation, which is based upon the bi-level optimization literature. This can possibly extend to both online and offline setting. And we have algorithm design analysis and so on. And then later, after I discuss this work, I will go back to the LLM, large language model, and see how this can be applied over there too. Okay. So some notations. Now you have MDP, Markov decision process. So S here are the state space. A here is the action. P here is the transition. Given a state and action, how the next state transits. So this is basically the environment. R is the reward, gamma is the discount factor, eta is the distribution of initial state. So this doesn't really matter, just for formality. Now, in terms of language model, state is the question you ask. Action is the sort of the response that language models provided. Now, if it's only single turn, then there's no transition. That's it. You're done. If there's multi-turn, it's a conversation. Then you'll have, so given a state, given an action, what it will be user's next question, right? So you'll have transition, right? So, but in most cases in language model, you don't have this. Typically, you don't have this. This is too complicated for them. They start with only one term. But in terms of reinforcement learning, people will consider this. So therefore, you need to interact with the environment. You need to know what the next state is, right? So that's a difference. That's or correspondence. And then, so okay, so I don't need to do this. So pi here, pi AS is to denote the policy, the probability of choosing an action under the state S, right? And then I use a pi E to denote the policy from the expert. So E here is the expert. So for this is basically for expert, given X, what will he or she do in this setting, right? So these are the sort of something that I want to learn from. So a classical formulation for this RAL problem can be written down as follows. So you maximize the entropy of the policy. So you want the policy to be as random as possible, right? So you maximize, this is log pi, st pi 18. And then this is tau A is sample from the pi, your own policy, right? So you maximize this. But under the constraint that the sum of all the features under pi is the same as the sum of all the features under pi E. So sorry, I didn't say that. So phi here is a feature vector of the state action pair. So you can later the reward model will be like a linear combination. Right? So at this moment, that's how they formulate the problem. They're simply saying that phi is given. All right, so this is a given. This is also given. You have an expert trajectory. I want to sort of match this. It's hard to explain because it doesn't have good intuition. That's why we want to improve from, but this is their formulation. Now, what they do is with this problem, this is a linearly constrained optimization problem. You could do a Lagrangian relaxation. So you relax this, you put in, you put a theta here. Theta is the dual variable here, theta, okay? You call this dual variable theta. You put it here, you'll have, now you will see you'll have theta times phi here. So theta times phi will now become your reward. And then when using this notation, I plug everything in, you will see that I'm minimizing pi, the difference between the two, basically the accumulated reward from the expert and accumulated reward from the agent, right? So I'm basically minimizing pi, and then here I'm maximizing theta. Theta is my dual variable. So this is their way of formulating the problem. Okay. So the thing is, the issue with this is that since linear reward only comes from the Lagrangian, they can only model linear reward. That's it. Right. So because this theta is Lagrangian, you have to linearly multiply theta with phi. So this is a linear reward. Also, this problem itself is not very intuitive. Why I want to match the cumulative sort of a feature with the expert feature. So we want to, our starting point is to improve this.
So means here, so could I use phi to be very complex, like network or something, which could be nonlinear, understand?
Yeah, so phi itself could be nonlinear. It's a nonlinear function of SA, but it's not an optimization problem. It's the feature. It's like the kernel.
So the kernel can also be learned like
yeah. So but they don't. So the only thing that you're learning is the theta.
Okay.
So our idea here is that so there are exactly two problems within this problem formulation. Why don't we just write them down explicitly, okay? In a single formulation. So there's the first task is the policy optimization, right? So for given reward, I want to find the best policy by maximizing the reward. The second task is reward estimation, right? I want to find the reward whose optimal policy matches the expert policy. Right? So these are two tests we want to solve at the same time. Right? Because in the end, I want to find pi and I want to find r. So then the formulation we have is using the maximal likelihood principle, which we're all very familiar with. The action generated by pi theta should be the most likely if the ground truth is expert policy. Right? So the maximal likelihood. So writing this down, it's like this. So this is the maximal likelihood, right? So this is the policy action generated by my policy probability, log probability. This is log likelihood. Sum over t of all the trajectory. So this is the log likelihood for the entire trajectory. The expectation is taken on the expert expectation, right? So this is a likelihood of this being matching the ground truth. Now, pi theta, why this is called pi theta? Because it's a parameterized by theta. Where is the pi theta coming from? Pi theta is solving the optimal policy where you have this reinforcement learning problem that we see before, right? So you have R, you have some penalty, but R here is parameterized by theta. This is the real theta that you try to find, right? So basically the problem reads like this. The lower level problem looks like a constraint, but itself is actually an optimization problem. I want to find, for given theta, I want to find the best policy that maximizes this problem. Now, the theta is still unknown. How do I find the theta? I put this back to another problem. I say that this policy you generated has to match the policy. Sorry, has to match the expert, right? And then overall, I maximize this theta, right? So this problem itself is called a bi-level optimization problem because you have two variables, two problems coupled together. One is my major problem, one is my auxiliary problem, and then auxiliary problem, you have an auxiliary sort of a variable here.
Yeah, so I'm not very familiar with IRL, but usually for RL, right, the policy pi is parameterized by theta.
You could parameterize that too.
So here, do you mean there's another
There's no.
parameter of pi?
Well, when you do the real implementation, people could also parameterize this. But if you write it this way, the only parameterization is theta. So this is auxiliary. This is a function of theta.
Okay.
This is a function of theta. And then this is a function of theta, and then this matches. So the main parameter is here.
What I'm asking is that in this constraint, right? So you want to solve this argmax over pi.
Right.
So does that pi parameterize by some other things? Right?
Good question. So now the question is how you actually solve this. So there are two ways. First of all, you could further parameterize theta pi using, let's say, phi, and then you like do gradient descent on this, right? So then you do this. Another way is, in fact, let me see if I have this. In fact, for this particular problem, you have somehow a closed form, more or less a closed form on this. So there is a closed form relation between pi theta, okay? So, but yeah, so in practice, you can parameterize this as well. Okay. So that's the problem, right? So this looks like a pretty complicated problem because you have two. And then so the problem itself is called bi-level. The upper level problem is to optimize the theta to fix expert, and the lower level problem is the entropy regularized RL. So the challenge here is that this problem is not convex. This problem is also not convex. Okay, so it's pretty complicated. Here are some specific solution structure for this. I'm not going to go into too detail about it. You can have a little bit of more analytical expression for pi theta. So this pi theta is, you can write it down. This is q theta is a q function. It's defined this way, and then something like this. But again, there's no closed form. You don't have a closed form for this. Therefore, you don't have closed form for this. Right? So these are just analytical solutions. And further, the BERT problem requires online interaction with the expert. So because here, this is pi e. So this is tau is generated from pi e. So I also need to sort of simplify this. So anyway, so we give but typically we will be given a fixed expert data, right? So the data is given offline. But then I don't have interaction with the expert as well online. So how to improve the IL formulation? So here we give a sort of a surrogate function. You don't really need to go into detail about it. This is an approximation of the previous one. And then later we show that the L hat and L is sort of a close, right? So they're close in terms of if you have a lot of data, then the difference will be small. So eventually we'll solve a sort of a surrogate problem, okay? But this is a sort of a technical detail that we don't need to really go
So
into.
you don't have access to expert data.
You don't have the online interaction. So you have the offline data. So the data is generated, right? So the data is already given to you. But you cannot interact with the agent real time. So there's a gap between the two as well. So, and then basically the algorithm is that with this formulation, what you could do is compute the gradient for the loss function. You can actually compute the gradient, but then the challenge here is that the optimal policy pi theta. So you need, in order to accurately compute this, you need to have pi theta. Pi theta is the optimal solution for the lower problem. So it's again the chicken and egg problem, right? So because everything is coupled. So we use our recent work developed for a bi-level optimization problem to solve this thing. So the idea here is very simple. So let's go back to here. So the idea here is very simple. So here is a lower level problem, it's a stochastic problem and everything. So I will fix my, so for this problem, I will fix theta, optimize pi by working one stochastic gradient descent step on this. So once you have an updated pi, it doesn't have to be optimal solution. It's just pi, let's say pi t. I'll go back here. I will optimize the gradient. I will perform one step of stochastic gradient for the upper level problem, and then go back. Okay, so that will be the sort of main idea here. So let's look at the algorithm a bit. So the algorithm here is basically two-step alternating. First, you will improve the policy by performing one step, which is called solve the policy iteration, by one step of the policy, improve it by one step. Right, so this is the sort of analytical expression for this. Basically, you work one stochastic gradient descent for improving pi for fixed theta, given the current for fixed theta k. Right? Once you have this improved policy, you go back to the upper level problem. You can compute the stochastic gradient as we just said here, and then update the theta for reward. Right? So theta k here is theta k plus 1 is a theta k plus alpha. This is a stochastic gradient. Okay, so a stochastic gradient. So that's, and then you alternate between the two. So basically the high level idea is that the policy update should be done together with the reward update for this problem. Okay. And then we have some theory for this. You could show that the pi will be close. So the lower level problem, although each time you only perform one step, eventually you will converge to the optimal step, optimal policy pi k for lower level problem. And then for the upper level, the gradient will be small. The gradient of the loss function will be small. Okay, so k is the iteration number. So that's really, the theory is really just there to show that the algorithm converges. And we have some special cases for linear reward. If it's a linear reward, basically everything will be very nice. You could actually find the global maximal likelihood estimator. So I'm not going to go into too detail about it. So that's basically linear reward. It's better. So let's look at some of the numerical results.
So yeah, I also worked on bi-level a little bit. So usually for bi-level problem, you have assumption for the lower level, right?
Yes.
It's usually strongly convex, actually. But earlier I remember you mentioned it's non-convex.
Yes.
So how are you going to deal with this?
So the good question. So so this is the thing that we actually need to. There's some special structure. I hide it because for this particular problem, the lower level actually has a closed form solution. But this closed form solution is you cannot write it down explicitly, but you can still. It's better than the typical bi-level problem. Okay. So you can, there's some structure you can use.
I see.
So even if you look at here, if you compute the gradient for the upper level problem, Hessian doesn't show. There's no hashing as well. So there's a simpler. So this problem is simpler than your traditional bi-level problem.
I see. Okay, there's some.
There's some structure you can use.
explore.
Very good question. So let's look at the numerical result. So first of all, since this is like an inverse RL, this is a standard sort of a RL, inverse RL environment. So this is the Majorco environment. You're sort of learning from these robots, right? So you're presenting how these robots walk, and then you're completing a certain task, and then try to mimic it. So these are different tasks. These are different algorithms, behavior cloning, and a couple of other algorithms. These are our algorithms. So these are the expert behavior. So if you have an expert knowing what to do, what the score they will achieve. The higher, the better. Everything is higher, better. We can see that our algorithm achieved pretty high score. Okay. The second thing is, since inverse IO, one benefit of inverse IO is a transfer. So once you learn the model, you learn the reward, it's easier for you to transfer to different environment. We'll also tested the thing. So we learn from a healthy ant, how it works. And then later we transfer it to a so-called crippled ant, where sort of the feet are shorter, right? So transfer learning, shrinked legs, right? So in this transfer learning setting, these algorithm is especially better than all the rest. So for these algorithms, they're only learning the policy. They're not learning the word. So if you're only learning, they call it imitation learning. You only imitate. If you only imitate the policy, then after you transfer, these policy doesn't work the way you work. It doesn't work. But for this, since I'm learning reward, I know where so I can easily transfer this reward I learned to this environment, right? So this is the transfer learning case. Now let's go back to the alignment problem, right? So now we see how to use demonstration data only to find a reward and optimize the policy. Let's go back to large language model, right? So going back there, we recall that there are two sets actually. There's one demonstration data and then one preference. And then and also as I mentioned before, in most cases, for language model, you only consider a single stage, meaning you don't have transfer. Once you ask a question, you get an answer, you get a reward, that's it. There's no transition. So this will make things much easier. So our formulation is the following. We can easily extend the previous bi-level problem to this setting where you have likelihood for SFT for the demonstration data, as we just showed. You also have the likelihood for the preference. Then you can add them together. This is the likelihood of seeing the data. So once you have the likelihood, again, the lower level problem is again related to pi, right? So you want to find the optimal pi with the reward. So it's a single problem where previously you basically separate them into three different cases. First, you do SMT previously, right? So heuristically, you do SMT first, you train this reward model, and then you solve a policy optimization problem. Now everything is together as a single problem. So pi is, so why they're connected together? Because pi is here, right? So when you have the SFT, so SFT loss here is here. So pi is here, and then reward is also here. So everything is connected, okay? So just a reminder, the SFT loss function is expressed this way, right? So it's a supervised fine-tuning loss. This is a reward loss, which is the log of difference of R, right? So R is here and pi is here. So everything is connected. So, and then there's a single problem, and then you can basically apply the same algorithm that we just mentioned. It's exactly the same thing. You first fix the reward parameter, you perform one step of optimization for pi. Once you have pi, go back there and optimize this loss, the upper level loss, and then go back and forth, right? So, so the new formulation unifies the three steps of our RHF into a single formulation. And the reward learning, especially this reward model itself, is able to learn from both the preference data and the demonstration data at the same time. So if just in case that some of the data set are not good enough, you're still able to learn from the other, right? So under certain, so this is sort of integrating all the data. The algorithm itself is also easy to implement. You only have two steps. You sort of alternating between reward and policy. It's not like separate steps, right? Okay. All right. So some numerical results here. So in this case, we use the GPT-2 as a policy model, and reward model is also GPT-2. And then we compare our AIHF. I call this a method alignment with integrated human preference, AIHF. Integrated means like the two data sets are integrated together. For this particular, the data set is IMDb sentiment data set. Basically, this is saying the data set is giving you a description of people's review of the data and asks you to predict the positive or negative of the sentiment. The second data set is the HH data set. It's anthropic, harmful and helpful, harmless and helpful data set. It's a conversation, but then the preference will be, so the data set, the human will prefer the helpful, will not prefer the harmful data, right? So this is another data set. And then sort of we see from, in this case, when we after start training, this is RHF, this is a 3-stage step. So this is the final step actually from PPO using the reinforcement learning. We're starting with the pre-trained model. We had a sort of a lower starting point. But later we're able to sort of increase much better for the averaged sentiment score. So this is basically accuracy, higher the better. Here, for the second statement, for the second experiment, we're evaluating the output of our model. So this is our model, this is RHF, by using a separate, a much more powerful reward model. So this is a 2B larger reward model. This is particularly trained on this data set. We're trying to see how good the generation is as we're going. We can see that for both cases, we'll be able to sort of increase the reward pretty significantly. Also, there are other, this is another setting, another experiment. We try to see how the reward learned from RHF or our method, AIHF, how this will be able to match the ground truth. So for both methods, eventually you'll get a reward. But then again, so since the heuristic, the RHF approach, you're only learning this from the preference data, which could be limited, which could be low quality. So the reward you're learning may not match the real sort of a reward function. Of course, here, this ground truth reward function, it's not human reward. It's still a sort of a GPT. So it's still this reward function, but we assume that this is being trained really well. So it matches the reality. But there's a significant difference between the two. And then for our cases, we're able to learn it. So so these are the sort of connection between the IRL and the IRL and the alignment problem, right? So basically, again, if you look at the entire problem, so basically what we're saying here is that if you could use the inverse reinforcement learning to integrate two different set of data, and then to use a single formulation to generate the reward and the policy at the same time. Okay, so that's the first set of the problem. For the second set of problem, I'll just briefly go over. So this is mainly trying to use zeroth order optimization to perform language model fine-tuning, right? So the alignment problem itself is fine-tuning, right? Because you already had a model, you want to fine-tune for certain purposes. But the fine-tuning problem is a much larger scope. There's many tasks you can fine-tune. So we'll briefly discuss how to reduce the computation and memory complexity of fine-tuning process, right? So there's the current state of art for fine-tuning is called parameter efficient fine-tuning. There are many different approaches here. Let's see. So there's 4 different main approaches. The first approach is fine-tuning the entire neural node, right? So you change everything. second is called LoRa, low rank adaptation. So what you do is, so this is your neural network matrix that you already pre-trained. You're not touching this. You're adding to this model by another matrix called B times A. So this B times A is a low rank. So both B and A are low rank. So this is N times R, R times M. Right. So overall, the total number of parameters is much smaller than M times N if R is small. Right. So this is called low rank perturbation. You're optimizing B and A, and then after you optimize B and A, you add back to them. Okay, so this is called LoRa, low rank adaptation. Also, there are sort of a prefix tuning, prompt tuning. So here you're adding something to the model. Okay, I'm not going to go into detail about it, but these are sort of 4 different ways of to do fine tuning. Now, the issue here is that even if you do all these parameter fine tuning, these in terms of memory, it's still pretty inefficient. Meaning, to do either one of those, the peak memory you need to consume is typically 3 to 10 times compared with if you only do inference. So the reason here is that if you do either of this, you need to do backpropagation anyway. So backpropagation is pretty expensive. So here is the experiment that we did on OPT 13B. So you see, if you only pass your data through the network, it takes about that much of a time. Well, so that much of a memory, 25 GB. But then if you do either SGD or Atom for all these different types of fine tuning, you see you either have 3.9 times that complexity or 10 times, depending on which case you're talking about, right? So then the question we ask is it possible to just use the forward pass? This is much cheaper, and then to replace these sort of gradient-based, backpropagation-based method to do fine tuning, right? So this go back to the optimization literature, where if you have the gradient, we call the method first order methods, right? So you're using gradient information. So here in fine tuning, first order optimization require backpropagation. Now there's also another class of methods called zeroth order optimization. So you don't need to have the gradient. You basically use the difference of the function values to compute the gradient, to approximate the gradient. So here U is typically a random direction, and then you basically evaluate your loss function at x plus mu U. Mu is a step size minus x minus mu U. Right? So you compute 2 value and then subtract and divide it by step size times the direction. This is your approximated direction. Here you don't need to do backpropagation. So there is a work published. It should be 2023, the NeurIPS, that's sort of applying this idea to fine tuning. Now, what we did in this work is we tried to benchmark all different kinds of zeroth order methods, and then try to see how efficient they are and how they compare with first order methods. Let's say want to do a benchmark. Here, there's no other new algorithms developed. I just want to understand the landscape. So you have, for example, zeroth order SGD, right? So you use this kind of gradient estimate to do SGD. You could also do a sign on this. You could also do momentum, or you do like an atom. Okay, so all different variations. So we tested it on all these different models, from smaller to big, relatively big, at different fine-tuning tasks. So here are some results here. So the zeroth order methods, so this is a particular task, SST2, this is a classification task. And then these are the accuracies. So this is the first order methods, all these are different zeroth order methods. And then these are 2 different models. So the first observation is that in terms of accuracy, they're okay. So first order is almost always better, but then we're not too much. So the zeroth order methods are not too much different, right? So, but then there's zero atom-based zeroth order is the most effective, meaning the accuracy much better, achieve the best performance. If you do SGD, it's not always good, and especially SGD, sign-based SGD, this method, you take a SGD, you take a stochastic gradient and take a sign. So this is the worst, okay, weakest. And then this is these are another set of results which basically says the same thing. But then the observation here is that if your task is very difficult, so this task we know Grandy. So this is the task that you're asked to generate. It's not only classification, but also to generate. So zeroth order methods is about 5 to 6% lower than first order methods. Okay. On the flip side of the coin, let's look at the memory efficiency, right? So this is the main sort of a benefit here. So zero optimize, so we're able to train all these different models on a single A100 for fine tuning, up to 7B model. And then it's about a third of the peak memory consumption compared with the first order methods. So this means that if you need 3 A100 to train to fine tune, now I only need 1. Maybe take longer, but need 1. Okay. So here are memory consumptions. So this is SGD. And then these are the so these are first orders, this is zero orders, right? So you see that if you do add them, this is a lot compared with this, right? So it's about 3 times bigger, right? So these are 4, 3, this is only, all these are 1, you can use 1 A100. So, and then if we further increase the sequence length, so this is number of sequence lengths you're increasing, you can see that the performance is also, so for zeroth order, it doesn't really matter for sequence length, but for first order, it increases significantly, right? So this is our basically first approach, trying to understand the pros and cons for different approaches. And then potentially later we could design better algorithms, maybe mix the 2 different approaches or something like this to strike the best balance between zeroth order and the first order. Okay. So I think I'm out of time. So I will skip the last one, but oh, by the way, we'll have a tutorial. We already had a tutorial on AAAI this year. We'll have another one on ICASP on this sort of entire thing about zeroth order methods and where the application is, especially the application in foundation model training. And then I will not go to the last part, which is about privacy, training private models. But if you're interested, I'm certainly happy to talk about it. Okay, so that will be all. Let me just briefly mention some ongoing work that we're doing. There's just 2 more slides. One ongoing work is that we're trying to understand the theoretical sort of landscape for transformers, right? So it's a very complicated problem because you have softmax, you have attention and so on. Try to understand how the geometry, how the optimization geometry looks like. The second one is about in-context learning. So language model has a very fascinating capability that Kevin also has been working on, which is called in-context learning. You don't need to train, you only need to give it some examples to provide the correct continuation. So try to understand how this behavior, why this will happen, and how this is related to the different model capabilities. Okay, so that's all. Thank you.
Any questions from the audience?
Yeah.
So in your roughly slides for this 3 or something, like you said you have 2 data sets like paraphrase and the demonstrated data set. Like,
yes.
You format that is bi-level. What if we only have 1 data set like a paraphrase one? Does it reduce to the DPU algorithm or yet do we have the closed-form solution for the inner like one?
So good question. So first of all, if you only have preference, you don't have demonstration.
Yeah.
You can remove this. These 2 problems are still coupled.
Yeah,
So
yeah.
you still have a bi-level. It's just, so that doesn't matter, right?
Yeah.
That doesn't matter. Now, you're referring to DPO. For DPO, what it does is that you solve this in closed form,
Because
you plug it back.
yes, yes.
So there's a gap somehow because your parameterization is different. Here you're parameterizing R, DPO you're parameterizing pi. But anyway, so if you solve this, plug it back in, you can still see that this is different than DPO because you're still utilizing both SFT
Yeah.
and RM at the same time.
Yes.
So in our paper, well, we're actually still writing the paper, but then in the paper, we actually had an specialization where you plug that in, you can see that this is also a sort of extended version of DPO, let's say.
I see.
Okay,
Alright, thanks.
Good question. Thanks for the presentation. I'm not an expert in this area, but I'm more interested in the applicability of this in real scenarios. So I appreciate the example of applying the expert learning for the autonomous vehicle scenario. So I was wondering, like a couple of questions. One is, do you have to make any special consideration if you have multiple experts? In a sense, if you have multiple drivers, so each one will have a different driving style.
very good question. So this is called heterogeneous data case. So this has nothing to do with the preference. So you have to go back to the sort of the IRL problem.
Yeah.
So this is called heterogeneous data problem. So yes, a special, you could treat them as the same. So let's go back here. So this is the likelihood, right? So you can treat them as the same, but typically their capabilities are different. So there's a small literature on this. So you could do EM, like EM type of algorithm to estimate which sample you are from which data, or from which agent. So this is hard, but it's important, but this is hard. There are some literature on this, so I can discuss with you offline on this. Yeah, so you want to identify experts on different, basically you're saying you want to identify experts on different capabilities, right? You have different.
Yeah, I mean, like if I drive different from.
Yeah.
So I'm
Yeah.
thinking like if I apply this in like a large scale where basically autonomous driving company wants to learn from their, from the drivers before actually, to fine tune to tune their.
Yeah, so typically over there, you could have, so let's say you have two experts, right? So you have two reward model to learn from. So here you have two reward models, sum together. But the question is, so which one you're fitting to? So so this is very relevant.
I guess you have to kind of compare.
You have to, yes, you have to compare, you have to also try to, you need to know how the combination is done, basically.
Right.
Okay. Yeah, this is a group. I can share with you the one
Yeah,
paper or two on
it's
this.
a very interesting. Just a quick question if I
Yeah.
have time. Very quick, yeah.
Sure.
I was thinking like if about like adversarial attacks, like if purposely make the wrong move.
So people have recently tried to attack reward.
Right.
They're saying that so for this entire process, the only thing you need to do is attack reward to inject some bad behaviors here, that this will be translated to learning from Pi. Yes, this is possible. And then there will be subsequent discussion of how to make this more robust.
Right.
This is, I don't think it has been done before, but it's a comment. People are starting to realize that too.
Thanks.
Other questions? Are people online?
Oh, yeah, sure. So me, like you would kind of say, okay, I like a way put this fine tuning and alignment together, right? So like what about training? I mean,
Yes.
and like what about pre-training? I mean, no, I'm so like I know like pre-training is very cost. I mean, but so like except for the costing thing is like why we have to do several steps or why put them
Yeah,
together?
that's, so the question is, is it possible to combine everything to single
Right,
step?
right.
So I guess the question is really the scale is different. So for training, the number of token you use is
It's good.
too much
Okay.
compared with whichever you do for fine tuning, right? So if you mix everything together, this it's not gonna work. But here in this setting, preference and demonstration are typically on a similar scale.
Okay.
Maybe 10 times different, the tops, right? But so therefore it's and especially the demonstration data is typically having good quality, high quality. But then if you look at this heuristic sort of a procedure, the reward has nothing to do with this high quality demonstration. You never learn from that. So that's the issue. That's the issue,
Mhm.
right? Okay. Thank you.
If no more questions, so let's give the.
Thanks.